before you even start so that you can see what it looks like. Sometimes when you graph it, you can see by the way the ends are behaving that something stopped this from going continuously through. So you can see kind of right here, this must be an asymptote. Things are writing right next to it. And be careful in your calculators. Sometimes in your calculator you can't get very exact, so you might see this. That's what you might see there. So just be careful. Maybe look at your table. Sometimes it doesn't get exact over here, or sometimes it gets like right on top of this line. Your calculators are not the best for graphing these. Kind of get the feel of where your asymptotes. I like to put the asymptotes down first, but that part you'll get used to. The first thing you should do always is find your domain. Find your domain restriction. Leave the range till later. Find your domain restriction. Go through and find your asymptotes next. So first find your domain. Look for restrictions in your denominators, just in case. Then find, God bless you, find your asymptotes. We were going to factor, but you don't have anything to factor yet. Factoring will start today. When you do your asymptotes, follow this list. Your vertical asymptote is what's left in your denominator, because you can't remove this out of here. This is stuck in here, and I can't use a 0. I took this out of my domain, so I got to kind of take it out of my graph. So the first thing I do is draw my asymptote here. Put your asymptote here. That's something I'm not going to be able to use. Because it's a domain restriction, you can never ever cross a vertical asymptote. What they're designed for is not only can you go over it, but it's designed so that the end behaviors will follow right alongside of it, but never, never touch it. So that's what an asymptote is here to do. Now, your horizontal asymptote gives you 3 things. The degree in the numerator. The degree in the numerator, the highest degree is a 1. The highest degree in the denominator is a 1. So you follow. If the degree in the numerator is equal to the degree in the denominator, then you make this line a ratio. You take their coefficients. So this would be a -1 over 1. This is the line, y equals -1. That's your asymptote. Use these rules. Remember I told you we would be getting rules for your asymptotes? These are them. Find this guy and map it out. Now, your horizontal asymptote also is there to guide your end behaviors. Look where your ends go. They follow right along, but they don't touch it. Now, there are occasions where this will cross over it. It will jump over it, but then come back and stay right next to the edge of it. And we'll see that. Because there's nothing stopping that from jumping over it. There's no domain restriction there. Asymptotes are designed to guide the end behaviors. Once you do that, you kind of know where your restrictions are. Find your range. You know that you can't use this y value of -1. We can't use this -1. But my graph goes from here, stops at the -1, jumps over it, and continues. So now you can do your range. Your x and your y intercepts, your y intercept is exactly the same. Plug a 0 in for x, but we can't divide by 0, so we had no y-intercept, which makes sense, right? Because isn't that our asymptote, our y-axis? Now the x, these are the zeros of the numerator. Follow your sheet. It's a little bit different than what we're used to doing. And today we're going to factor, so you're going to see a little bit of a difference. So take your numerator, set it equal to 0, and this is your intercept. And when you graph it, when you sketch it, you should kind of see it pass through there. That's what helps you do this, because sometimes your calculator doesn't really do a great job with it. Again, we said yesterday there's no min and max in this one. You know, the highest and the lowest go by the end behaviors. But you do have a concavity, and if you go left to right, as your x increases, your y decreases. Thank you, love. As your x increases, your y decreases. So you have 2 decreasing sections. We good? Gabby, you missed this yesterday. Are you seeing this? Follow this sheet. Stop me if you have any questions. This is kind of basic. We changed this up on you a little bit but it's still following through piece by piece.
Wait, can you explain why there's no inflection?
Why there's no inflection? There's no inflection because there's no turns that connect on this. We get an inflection when we go like this, when this shares this, but they don't share any curves. And we don't even have we don't have a max or a min here either, so they don't like come up and come back down. These actually keep decreasing and then go like this. So there's no technically max and min. This is your max and this is your min, but these don't give us. If they went like this, then yeah, we would have a max or a min when they do this, but we still wouldn't have an inflection. An inflection is when you have a set of terms and then they connect. These are not continuous. Where the other functions we were continuous, this is still a function. It still passes a vertical line test. This is still a function, but we don't have any max and mins on this guy. All right, this one, you got to do something with that negative out there. That negative has to belong to somebody, so I chose to put it in my numerator. Otherwise, if you do your zeros of your numerator and you do your denominator, you lost your negative. So when you graph this, it's almost the same kind of concept. We still have asymptotes. So first thing, find your domain restriction. Always look for your domain restrictions first. We can't use the -4 in the denominator. So I map out my asymptote here for x is equal to -4. Start like that. Now do something with this negative. I distributed it across the top, or just put negative x plus 2 in parentheses and work from there. Find your asymptotes. We found your denominator one. Your horizontal asymptote says take the degree in the numerator, the degree in the denominator. Again, they happen to be equal. It's the second line when they're equal. Use their coefficients. Because I distributed the negative, it's -1/1. And you can kind of see on your graph what's happening to it, right? Can you see it there, where it's going? Work your intercepts, same way. Your y-intercept, just plug in an x of 0. Your x-intercept, this is zeros of the numerator. Again, we have no max or min. It looks the same exact as the other one. These are, again, both decreasing and concavities. Concavities might be harder to see. This technically is a cave up. Even though it's not coming back up, it's technically a cave up. The cave exists up here. This cave kind of down here. Think of it that way. Yes? Increasing is going to go the opposite way. If you have this, and then this. So as your x goes this way, your y is increasing, and then this would also be increasing. Good? You just have to kind of get used to these. This one, again, look at your denominator. You can't use a 0. So right away, that becomes your vertical asymptote. You have nothing to factor yet. So that becomes your vertical asymptote. God bless you. And here's your other one in here. Zeros, check your horizontal asymptote. There's an x to the 0 up here. Because anything to the 0 is 1. So technically there's no x, so it's x to the 0. When the degree in the numerator is less than the degree in the denominator, we automatically have a y equals 0. Automatically. That's your x-axis. I think that is the first one. If your degree in the numerator is less than the degree in the denominator. We only really have two things you have to check. If it's less, and so far if it's equal. Today we'll do what happens when it's the last one. So we've got this. So right now here's your asymptotes. This guy and this guy. And then we say your x-intercept, plug a 0 in here. Well, we can't do that. We have no x-intercept, and we have no y-intercept. We have no zeros of your numerator for the x. And the y, we can't do that. So we have no x or y-intercept. No max, no min, no inflection. This has an increasing, this one, and this has a decreasing, that one. They both cave up. graph helps a lot. Well, you can find your asymptotes. You can find your asymptotes first, and you can map out your asymptotes. So if I was going to graph this or try to graph this, all I know right now is that here's my asymptotes. This is all I know right now. I know I can do my intercepts. I have no x in my intercept, but I can kind of see that because I have these are my asymptotes. Where it goes, I don't know. I have no way to figure out where it's going until I graph it. Right. It's a little tougher. Like, think of it this way. If I were to bring this up, if I were to come up, this would be my concave up. It would make like a U. When it's down here, think of just joining it down here. That's bringing you a concave down. I remember when I first learned these, and I didn't even remember learning concavities. So when I was teaching this, like 8 years ago, I'm like, that doesn't sound right, this concavity thing with it when it's like this, because there's no max, no min either. So I looked in many books to see, and they all say this is a concave up when it comes out like that. So I guess we have to go along with it. I disagree with it, but I don't write the math books.
Is there never a max or min for these?
There will be. Not right now, but today's work will be. These we just had straight graphing just to get you used to asymptotes. Today you'll see it. Okay, again, the denominator, even though it's a cube root, set it equal to 0, and you got 3 of those things, you still can't use x is equal to 2. So x is equal to 2 becomes your domain restriction, also becomes your vertical asymptote. Your domain restriction and your vertical asymptote exactly the same for now, until we factor. Your horizontal says the degree in the numerator, which is an x to the 0, is less than the degree in the denominator, which is an x cubed. So y equals 0 is automatically an asymptote. When you do this, when you do these guys, it helps confirm where your asymptotes are. So when you do an x-intercept, you go for your zeros of your numerator, there's nothing up there. I can't have an x-intercept. Even if you did it the other way and you set it equal to y. As soon as you crisscross this, you're going to see this. This is really zeros of your numerator. We haven't factored, so it doesn't matter yet, but you'll see it today. And we have no x's in our numerator, so we have no x-intercept. And that kind of confirms, yeah, there's my asymptote, God bless you. My y equals 0 is my x-axis. I can't have an x-intercept. My y-intercept, I plug 0 in for this, and I'll find my y-intercept. Again, decreasing, decreasing. No max, no min. Just concave.
Is there ever an inflection?
And these, probably no, because they're probably, they're cut apart by asymptotes. I can't remember that we have an inflection point on these. We could have a really weird looking one, but I doubt it. Because they're usually cut apart by asymptotes. It's still a function. Just a little different than you're used to looking at. Are we good with this? And is this the last one? That one.
This one is good.
Oh, this.
I drew it, but I didn't know how to find like increasing.
Okay, so let's work this one. Now this is a good one. This was the one I started to do with you yesterday. This was the one like in class. Only it went this way, didn't it? It just went the other way. It went through and it went the other way. This is a good example of it crossing the asymptote. Look at this piece right here. It crossed right over your horizontal asymptote. There's nothing stopping it from crossing. It crosses your horizontal asymptote here. Oh, hang on. It crossed your horizontal asymptote. My graph is a little bit off, but right there. Now, it can cross that. It can't cross a vertical. Vertical, it can't cross. Bless you. Verticals come from your denominator. Can't happen. It can cross a horizontal one, but it can't cross a vertical. And these use this one as guidelines. You can factor these. We're not reducing anything yet. and put these, this is your domain restriction, find your plus or minus 2. This is also your vertical asymptotes right now. So here's 2 asymptotes. Your degree in the numerator is the same as your degree in the denominator. So take those coefficients. So y is equal to 1. These guide this end behavior right here. This guides this end behavior right here. I can cross this. Increasing, decreasing, this guy, as you read x from left to right, this is increasing. This is also increasing. This is also increasing. I have 3 increasing. Remember, you're reading x left to right. You're looking to see what's happening to your y. Your y is increasing as you go left to right. Your y is increasing. Your y is increasing. So you have no decreasing. I didn't even put it up here, huh? You have no decreasing. You just only have increasing. So you're increasing from negative infinity to negative 2. You're increasing from negative 2 to positive 2. And then you're increasing from 2 to infinity. This, here's an inflection point right here. This is an inflection point. Because what happens is this is the hardest inflection point to spot. I'm coming along from the left, right? I'm going like this. I technically should have came down here, but I changed my mind and I went up instead. That's an inflection point. Because that's where it crossed the X, that's where it crossed this spot right here at the 0, 0. Go in your calculator. Yeah, go in your calculator. X, where's where the X intercepts? It should be here as well. Here, it's here as well. Your Y intercept and your X intercept. It should be there as well. Algebraically, it should be in your intercepts. And this is a good way to check to make sure everything is on schedule there. Your intercepts should match what your graph says. It should match, all these things should match. If something doesn't, and that's why it's good to do your intercepts algebraically, because it'll tell you if you're off or not. Okay, so let's cross this. Alright, the first thing we're going to do is factor everything. And then we're going to find a domain restriction. So, this guy can't be factored, right? Can I factor the numerator? No. Okay, so I take this guy, I find my domain. So when x is 2, I have a problem. So I take 2 out of my domain. My range, I wait. Now, because you know your domain, let's figure out your asymptote now. Your vertical, let's go to your vertical asymptote. I can't factor anything. There's nothing to factor. So I go to my vertical asymptote. My vertical asymptote is x is equal to 2. So when I graph this guy, I'm automatically going to have an x is equal to 2 in here. Good so far? Okay. Next thing, let's go to your horizontal asymptote. A horizontal asymptote says the degree in the numerator compared to the degree in the denominator. This 2 is bigger than 1. It's the last one of the 3. If the degree in the numerator is greater than the degree in the denominator, 2 is greater than 1, then we have a slant asymptote. And we have no horizontal asymptote. Well, then we have no, let me put it this way. We have no horizontal asymptote. So no horizontal asymptote. Then we check, and we say if the degree in the numerator is exactly 1 more than the degree in the denominator, now we have a slant. And I just abbreviated by SA, slant asymptote. Asymptote's a long word. What this is when the degree in the numerator is 1 more than the degree in the denominator. 1. 1 more. Exactly 1 more. 2, 1. What's that? what are you missing?
I said just, yeah, you can just keep going.
No. I need you to understand this. We do a domain restriction. We say we found our domain restriction. That's the same as our vertical asymptote right now, right? Then we check for horizontal. According to your sheet, there's no horizontal asymptote. Now we have to check for a slant. You didn't do this before. Good, here we go. Oh, okay, that's what Rosa told me. Thank you. Oh, it was, and I only had two, and then one of the two. I did. I do algebra. Oh, I see. Not APS. Okay. Thank you, Rosa. Thank you. Okay. I need you to see this flow. Good?
Yeah.
Vertical, horizontal, no horizontal. The only other asymptote I could possibly have is a slant. This is new today. Slant says if the degree in the numerator is exactly one more than the degree in the denominator, I have a slant asymptote. Now, my slant asymptote, this is how we find it. It synthetically divides. Ah, yes. Watch how easy this is. So pull out these coefficients. 1. What else? -2. 4. What should I divide by? 2. My 0. This is my factor. When I set that equal to 0, I find the 0, the root. So I pull this down. 1 times 2, 2. 0, 0. This is my remainder. Now, the nice part is, I don't care about my remainder. Very nice. And because the degree in the numerator is exactly one more than the degree in the denominator, this x comes out to be x to the first. So this always comes out to be a line. Aren't your asymptotes lines? So far, this doesn't always, I shouldn't say always. Sometimes there are some that it comes out to be a parabola, but right now it'll come out to be a line. So we have the line y equals x. So I'm going to do that, and that's a line that cuts through here. This is my line, y equals x. Okay. Let's see how much we can get through without actually graphing this, and then we can see what we're looking at. Okay, let's do the intercepts. A y-intercept when x is equal to 0. I have a 0, 0, 4. I have a 0, -2. So my y-intercept should be a -2. Good? Good so far? Okay, so I should be crossing at -2, 0. That's where I'm going to cross my y. My x-intercept, stay with me, says zeros, oops, except for my board, says zeros of the numerator. So now I have to do zeros of the numerator. You can use the quadratic. You can use complete the square. You hate complete the square? Complete the square is nice when this is even.
I know some.
Okay, so instead of having you work that whole thing out, you can use quadratic, you can use complete the square. We're going to find out that this has no real, it's imaginary, it has no real roots, no real zeros. It's imaginary. That's as far as I need you to go, because we're on a real graph. We can't graph the imaginary roots. So right now I know I crossed the y-intercept somewhere over here, and that's all I know from this. But because I can figure something out, I know this graph must go like this, because it's in this section, isn't it? If it's in this section, where else do you think it is? If my graph goes like this and crosses this, where else do you think it is? I only know that because this is the only piece of information that I know. I know, hang on. There's no x-intercept. Okay, hang on, so it's gonna...
It's not negative.
Oh, that's not -2, 0. Okay, change my mind here.
Just with the y is wrong. It should be 0.
It should be 0, -2. Sorry about that. Nobody stopped me. I talk too fast when I go. Okay, so this is going to pass. It's no real intercept, so I can't erase this. So this is going to go like this. It's going to come like this. I got to cross this, and I'm not going to hit the x-axis, so it's got to go like this. If I'm here, this is all that my information tells me. I only know one piece, and I know that I don't touch that x-axis. So where do you think my other piece is? Using my slant asymptote. Up here. Up here. Is my slant asymptote there to guide my end behaviors as well? What else is guiding my end behaviors? My vertical asymptote. So my asymptotes are going to guide my end behaviors.
So it's going to be in between where they thought?
It's going to be, yeah, this kind of like makes an X, if you will. So they're going to go like this. Well, because I knew that, because I knew this one point, and I know that I don't touch the x-axis. That was my mistake over here. I know that I don't touch the x-axis, and I know I crossed that point. And my asymptotes guide my end behavior. If I put my graph over here somewhere, just right next to this, this is an asymptote. This says, hey, stop, you can't do that. You can't go past me. You're going to have to go alongside me. This guy says you're going to have to go alongside of me up here. So it kind of gives me a feel for where my graph is. Graph it. And then you can graph it, and you can see that. Okay? You are going to have to find a max and a min on this one using your graph. Why? Because here is my relative max. Here's my relative min. Do you see where it is now? Relative max and min. I've got relative min over here. Let's call this A. I've got a relative max over here. Let's call this B. These guys, remember when I told you when we had slants, they'll do the max and the min. Then they'll also do concavities, and we'll do increasing, decreasing with these guys. Yes?
I look at the other parabola thing.
You might have to move it. You might have to change your window.
Oh, shoot. Never mind. I didn't.
Try not to do zoom out and zoom in. Try to go and change your windows. Also, guys, what you can also do when you graph this in Y2, put the line Y equals X. Put your slant asymptote there. And if you had a horizontal asymptote, you could put your horizontal asymptote on your graph. You can't put your vertical because it's X equal, but you can put your other asymptotes there. It's a good idea to put your slant one because you'll see that your graph doesn't cross over it. It's just going to use it as a guideline. So what do we have left to find? Your relative max and min, if you don't mind, I'm just going to say this is the relative min. It's 4, 6. And this is the relative max. It's 0, -2. It was right here. So we were pretty darn close to getting that graph. It was at that point. And then your concavity. Your concavity is going to go from your concaving up. This makes a perfect cave. This makes a perfect cave. Increasing, decreasing goes from here to your point, right? And then decrease. Decrease, increase. You got the increasing, decreasing down? So let's increase from -infinity and stop here at what value? 0. Then from 0 to where am I decreasing? 2. Nuh-uh, +2 right here. I'm on this leg right here. I'm decreasing. Then what am I doing? From here, from my start up here, what am I doing? Decreasing. From where to where? 2 to 4.
Yeah,
So there's my asymptote. So that's like, I can't go past that, right?
how do you get
4 is my turning point. 4 is my turning point. Remember, these are x values, not y values. And then, I forget where I left off. Then we're increasing from 4 to infinity. Okay? Concavities, these are concavities. No inflection points because they're not joined together. They're two completely little caves.
Wait, what are the
Concavities, this is your concave down. Concave down. Where am I concaving down from? I'm coming from here. From where? Negative infinity. And where am I going to stop caving down? 2. Yeah, but that's my asymptote. That's my natural boundary. I can't go past that. And my concave up says what? 2 to infinity. That's it.
what's the range?
The range. Find the range now. Okay, so find the range. The range comes from here. The range comes from negative infinity. Where does it stop at? What's this point? Negative 2. So from negative infinity to negative 2, then I take a jump over here, right? Because there's nothing in here. Where did I restart my range? 6 to infinity. Like I said, you might have to do your range last. Because your range is a little bit difficult. We'll get to that. We'll get different pieces of information, and we'll have to make an equation. But one step at a time. Are we seeing this? The key to this, guys, listen to me carefully. The key is first factor whatever can be factored. Okay, factor and reduce whatever you can factor. What's left, we'll always find your domain first. After you factor. Then when you reduce, go to your vertical asymptotes. Then do all your asymptotes. And sketch it out with your asymptotes. And then put it in your calculator. Because sometimes your calculator doesn't really do this justice. It's kind of hard to see where does this thing go, where did it stop. But your asymptotes will guide you. Yes?
Will you tell us what we have to label?
Of course. It will be the same thing as that mess that we used to have. Okay, I'm going to cut your homework down because we did do the point of discontinuity. So hang on. Let me tell you what to do for homework. I don't know what I gave you. Okay, I want you to circle these guys. Hang on. You're only going to have a couple to do. You might even have less than that. Do number 1, and number 5. Oh. And you can do number 3. Number 1, 3, and 5. I'll tell you right now, 3 is like what we did yesterday. 3 looks exactly like yesterday's work. You guys listening? 3 is like yesterday's. So it doesn't have a slant, but it'll make you have to think about going back to what we did. Okay?